Hello, everybody. First of all, hope everyone is keeping well during this strange time. My name is Ray Song from Hydrock Consultants. It's my pleasure to present in this technical conference. The topic of my presentation is CFD investigation of fire-driven airflow within cavities behind the perforated cladding system. The outline of my presentation will include the introduction of the topic, discussing around the fire safety issues within the cavity space within the external wall construction. I'm also talk about the application and benefit to the perforated cladding system. Then I will present the CFD analysis and the result that we have up to date for the investigation, followed by the conclusions and further studies. The Grenfell Tower tragedy has highlighted the severity of the fire spreading over the cladding. It is considered as a significant life safety risk, especially for the high-rise residential buildings, and highlights the importance of the fire safety design of the cladding system to prevent the fire spreading on and within the external wall. The tragedy has led to the new regulatory change in the UK to restrict the use of the combustible materials in the high-rise buildings within the external wall, and also the provision of the adequate cavity barriers within the wall to enhance the fire safety provision to the building. Dam Judy had to report also highlight the steps to further enhance the fire safety to the building and highlight the importance of the risk and outcome-based fire safety design in the building. Therefore, a better understanding of the performance of systems in fire is essential for a robust fire safety design. The study presented in this presentation aims to understand the fire-driven flow within a cavity created by a decorative perforated cladding system. As you know, that once a flame began to impinge upon the external fabricate of the building from either an internal or external fire source, there is a potential for the external cladding system to become involved in fire and to contribute to the external fire spreading of the buildings by one of the following routes, or a few of them. The surface propagation. This influences the rates of the fire spreading of the building envelope by the way the surface of the external cladding system. Combustible materials such as insulation materials, without any doubt, will provide a bypass for fire spread and accelerate the fire spread rate as well. It could also spread across the building via the attachments to the external wall, such as combustible balconies. The other very important part is the cavity. Cavities are common in external wall for different purposes. It can enable the drainage and the ventilation, and also limit the internal passage of the moisture. However, extensive cavities have the potential to spread the smoke and flame in an unseeable manner from one compartment to another. If the flame become confined by entering the cavity with the external cladding system, they will become elongated as they seek oxygen and fuel to support combustion process. This is known as the chimney effects, which can lead to a fire extension for many times than the original fire length. This effect, even if within a cavity that is fully non-combustible, could also allow the flame to reach the next floor level, where if there's windows or any other wall penetrations allow the fire to re-enter the building. That will cause the fire spreading from one level to another, causing the breach of the compartmentation. Perforated metal cladding is increasingly applied in different type of buildings, as it provides a very effective way to enliven the facade of this otherwise simple structure or building. The perforated cladding has ability to add depth, texture, or features to the facade. Since the form of the perforation is variable and attractive. It can also control manage the amount of natural lights reaching the inside of the building, relying on the size of the perforation, but reducing the amount of solar gaining, especially for the building with large glazing elements. However, the perforated decorative cladding creates the cavity or gaps between the metal cladding and the wall, which could provide a potential fire spreading path due to the narrowed space. But in the meantime, due to the perforation on the cladding, the air inflow differs from the cavity within the traditional ventilated cladding system, which may differs the fire dynamic within the space. And this slide is a simplified way to demonstrate the key phenomenon that happened in the cavity. The fire behavior in a narrowed cavity scenario with no perforation is governed by the limited space under the chimney effects. The ignition and the efficiency of the combustion is controlled by the rate of air inflow and pyrolysis rate if there's any combustible materials in the gap or the wall surface. The flame geometry, the flame height is likely to be influenced by the cavity width. Heat transfer from flames, radiations, effects from the cavity enclosure from some of the cladding will determine the heat rates and heat areas in the space as well. However, with the introduction of the perforation on the cladding enclosure, the air inflow rate will be increased with the perforation rate increases, and the re-radiation from the cavity enclosure is also reduced due to area reduction of the enclosure of the cladding. In the meantime, the perforation also provides a way of heat dissipation to the outside of the cavity. However, there's very little study has been carried out for the fire-driven flow within the cavity behind the perforated metal cladding. Therefore, in this study, we use the CFD as a tool to study fire-driven flows and the flame spread within that kind of cavity. A series parameter study was carried out based on the CFD model. The model is consisted of a narrow and long gas burner, which is positioned between two parallel facing non-combustible surface, one representing the outer face of the wall construction and the other representing the metal decorative cladding. The dimension of the model is assumed to be 2 meters by 1 meter. The burner is located next to the wall, and the outer face of the wall is assumed to be of brickwork construction with 120 millimeters thick, and the perforated cladding system is assumed to be of steel material with 10 millimeter thick. The temperatures, incident heat flux, and upward airflow air velocity within the space are all measured. The parameters that has been investigated include the cavity depth, perforated ratio, and the fire intensity. 3 different cavity depths, 40 millimeter, 80 millimeter, 120 millimeter were studied. The perforation ratio ranges from 0% to 50% for the comparison purpose. A case with no metal cladding were also studied. The fire intensity studied was 50 kilowatts per meter, 30 kilowatts per meter, and 150 kilowatts per meter, which are comparable with the available test data, fire test in the literature for small scale cladding fire tests, where the heat flux ranges from 16 kilowatts per meter and 125 kilowatts per meter. It is of course knowledge that there are limitations to the study. First of all, the perforation configuration, such as the size, the location, the shape of the perforation, may have different impact on the fire airflow pattern within cavity. However, this study focused only on the metal cladding with vertical perforations. The fire scenario used in the study may not be the same as that fire from a postal flashover from a compartment. Under the simplified arrangement, does not consider the cladding supporting system and any other construction details. However, this study is aimed to only understand the fundamental principles and the parameters affecting the fire dynamics within the gap between the perforated cladding and the non-combustible wall surface by a simplified model with a reduced dimension. Further study will be carried out for a more complex or more realistic fire scenario in the further studies. As of every CFD analysis, the first step is to establish the suitable mesh size for the purpose of the study, considering the balance between the level of accuracy and the computational costs. A sensitivity study was carried out to compare the result obtained by using different mesh sizes, such as 5 millimeter, 10 millimeter, and 20 millimeter. The deviation of the result is presented in this table, where it shows that the deviation from a 10 millimeter and the 5 millimeter mesh size is by large less than 10%. Although it's not a perfect match but for the purpose of this study, which is preliminarily understand the fundamental principles and parameters that affect the fire-driven flow within the cavity by a comparative study, we consider that 10 millimeter mesh size provides a acceptable level of accuracy and fit for the purpose of this study. The following few slides shows the results of the CFD analysis in order to demonstrate the impact of different parameters on the fire-driven airflow pattern within the space. And these slides present the flame height within the space behind the metal cladding with different perforation ratios, including 0, 10, 25, and 50%, and a case of no cladding system as well. The depth of the gaps is 40 millimeter. It can be seen that the flame height is reduced significantly due to the perforation on the cladding, and it can also be seen that the flame can be elongated with the enclosed cavity with no perforation. However, when the perforation ratio is above a certain level, its impact on the flame height is reduced significantly. This slide shows the velocity contour at 20 seconds of the case for the cases with different perforation ratio, where the fire is in a steady state already. It can be seen that the velocity within the airflow within the space is clearly reduced as the perforation ratio increases. With the perforation ratio more than 50%, the velocity of the air-driven flow within the cavity is very similar with the case with no cladding. So that means if the perforation ratio is over 50%, then the impact of the cladding on the airflow velocity within space is less significant. This slide shows the incident heat flux and temperature that was measured along the height in line with the central line of the fire. The incident heat flux was taken as a sum of the average radiative and convective heat flux measured at each measure device between 10 and 40 seconds, where the system is considered to be in a relatively steady state. It clearly shows that the cases with no cladding cases and no perforation cases provides highest incident heat flux than all other cases. This is likely to due to the effects of the re-radiation from the outer cladding panel with no perforation, as well as the increased temperature within the cavity where there's no perforation providing, heat dissipation to the outside. However, with the cavity, when the perforation ratio is over 50%, the incident heat flux along the height is very similar, with the case with no cladding. Again, it's demonstrated that with the perforation over 50%, the incident heat flux and temperature was not influenced that much by the provision of the cladding system. This slide shows the impact of the cavity depth on the fire-driven flow velocity. The velocity was presented here, represented by the isosurface of velocity 1.5 meters per second. So there are two groups. Figures are shown there, each of which are having 120 millimeter, 80 millimeter cavity depths respectively. Within each group, there are 3 perforation ratio cases were presented. It can be seen that in general, the impact of the cavity depths on the velocity of the airflow is less significant than that of the perforation ratio. This is due to the perforation has more direct influence on the air inflow rate to support combustion within the cavity space. And this slide shows the incident heat flux of 2 perforated two cases with different perforation ratio, i.e. 25% and 50%. Within each plot, the results are provided for different, cavity depth. It can be seen that the incident heat flux along height within the cavity does not vary too much if the perforation ratio is over 25% and the cavity depth is more than 80 millimeter. And this is a temperature of the airflow within the space represented by the isosurface of 200 degrees centigrade to show the influence of the cavity depth on the temperature within the cavity. It can be seen again that as the same pattern of what we seen in the velocity slide, the impact of the cavity depth is less significant than that of the perforation ratio, especially when the cavity depth is over 80 millimeter. So this slide shows the impact of the fire intensity on the fire-driven flow within the space. Clearly, the velocity, temperature, and incident heat flux all increased with the fire intensity increases in the space. But if we also look into for the case with the most severe fire intensity, we also look at the impacts on the perforated perforation ratio on the fire-driven flow pattern within the space. That is presented, the velocity and the temperature plots this is the velocity are presented in these slides. It can be seen that when the perforation is over 50%, the fire-driven airflow within the gaps is similar with the case with no cladding, i.e. the influence of the perforation ratio on the fire dynamic within space is reduced when significantly reduced when the perforation ratio is over 50%, even under the most severe fire that we studied. So this study presented in this presentation is a preliminary study on the influence of the cladding perforation on the fire-driven airflow within the cavity. It's only aiming to understand the influence of key parameters on the airflow pattern within caps, based on the assumed fire size and the cladding configuration. We plan to investigate the performance of the cladding system further by carrying out CFD modelings with full cladding system under more realistic fire, for example, post flashover. We also aim to study the cladding system with different perforation shapes and locations and ratios as well. With that, this is the conclusion of the study we have up to now, which I basically have talked through already. So due to the time limit, I'm going to stop here and thank you for listening. And if you have any questions, feel free to ask. I appreciate any feedback for that. Thank you.
All right, here we go. So we'll just keep an eye out in the session chat for any questions coming in. Mm-hmm. Yeah, thank you very much for your talk. Appreciate it. It was nice. Yeah. Okay, so we have a question here. Did you have a chance to validate the model with any experiments or literature data?
No, but that was the intention for the next step, because that was the, I know that there are a bunch of, available test data for the traditional ventilated cladding system available there. We wanted to do some sort of verification, validation, and assessment against the experiment data. But again, I don't see any at the moment any perforated cladding system has been tested. So we probably just need to sort of kind of do a bit of validation, verification the model based on some traditional ventilation system, and then tweak our model again. To investigate the perforated cladding system there.
Great. And then,
well, hopefully there will be some universities or any research program that will be doing the test data, because we're working at I'm working consultancies. I don't think the company would pay for that anyway. So
right. Yeah. Good. There's a shout out to anybody looking for their next thesis or something.
But hopefully we can. There are a couple of good universities we have a relation with, so probably some worth a conversation with them maybe next step.
Great. And then a question about how did you reproduce the perforated area on the surface by means of maybe porous media, or how did you do that? Wonders how you reproduce the perforated area.
Right. Okay. So, well, the perforation that we created in the model is relatively simple for that study. Is just a vertical perforation that we are trying to study there. So the way we created that is by creating holes onto the objects in FDS.
Okay, great. And then did you look at the impact of the perforations in combination with vertical and horizontal airflow around the high-rise building? And that kind of follows into another question about, was windage considered in the model? So looking at the wind effects.
At the moment, no, because we're trying to sort of consider basic principles first. And the next step will be obviously when we were trying to model the more realistic fire and also the wind conditions, and even more different type of perforation shapes and locations as well. These will be considered.
Great. Somebody's thoughts here for future analysis would be to introduce cavity barriers and see how the cladding perforations impact that, and like would the flame jump over the barriers via the perforation, just kind of bypass it. So
definitely.
Last question here, because the wind effect was answered already. Will there be any difference in flow of smoke if we use sprinklers on the facade? So that's an interesting.
Question. At the moment, I'm not aware that any sprinkler system has been available in the market to apply to the facade only. But the fire scenario we're talking about is from a room. So, I mean, where if the sprinkler will be able to control the fire within the room. But once it's reached to the cladding, at the moment in that study, was not considered.
Okay. Well, good. Well, that's a good stopping point. Thank you very much, Rui, for your talk and for participating here in the Q&A, and we'll see you in the event. Thank you.
No problem. Cheers. Cheers, guys.